Okay, so back side of our notes. I stopped it. I'm hoping that'll cut down on the number of skips. So there's two little typos on this page. So in the first problem, there's not two natural logs, and same thing in the second problem. That's just something that happens sometimes. Okay, so we're going to cross those out. All right, so let's look at this. One formula that can be used to determine the change in velocity of a rocket as it burns fuel, I can't even say that, is the Tsiolkovsky rocket equation shown below, where delta V is the change in velocity and VE is the velocity of the exhaust, M sub 0 is the initial mass, and MF is the final mass, okay, with no fuel. So we first have fuel in the rocket, then we don't have fuel. This is our change in velocity, how fast we're going. Okay, so if delta V is 9,700 meters per second and the velocity of the exhaust is 4,500 meters per second, determine the ratio of the initial mass and the final mass. Asking for is this ratio. What is that ratio? It's not asking for MO or MF, but the ratio, the total of that. Okay, so we're just going to plug and chug here. So we plug in and we get 9,700 equals 4,500 times the natural log of M sub 0 M sub F. Okay, we don't know any more than that. So we do what we've been doing. We divide out the 4,500. Okay, we're just going to divide this side by 4,500, this side by 4,500. Okay, put that into our calculator, and we're going to get 2.1556. Okay, goes on, and this is 2.15 repeated, equals the natural log of M0 over MF. Okay, so here I am, and now I need to solve this. So I think I look at this log, I got to get rid of it. What am I going to do? I'm going to exponentiate. So I write E, I just make it an exponent, and on this side I make it an exponent. Okay, these two will cancel, so I will be left with the ratio that I want. MF is equal to the number on my calculator. Now, what I'm going to do to make this more exact is plug in E, blue key, E is over here with the divisor, the E, raised to, and then I'm going to say, parentheses, 9,700 divided by 45, because that's where that long number came from, was those two numbers divided. Okay, so now I get 8.633. Okay, well, actually if I round, it should round, yeah, 8.633. 8.633. All right, and that's my answer. That's the ratio. Okay, and I could, if I wanted it in ratio form, I could say math fraction. Okay, well, I'm giving the same thing. Or I would do fraction. I'd have to say 8, and what's the fraction? It's approximately 2/3, but doesn't matter. That's what I need. Okay, last problem. The moment magnitude of an earthquake is energy in ergs and can be modeled by this equation. So, in 1906, which would be we need it, a powerful earthquake took place in San Francisco. It had a moment magnitude of 8.3. So we've got an M value, right? That M equals 8.3. How much energy, that's what I'm looking for, that variable, did this earthquake release? All right, so I'm just going to substitute. 8.3 equals 0.291 times the natural log of E plus 1.17. Okay, we're going to do what we're doing. Subtract the 1.17 to get 7.13 equals, there we go. Now we're going to divide out that constant. Okay, they'll cancel. I'll get the natural log of E to 24.502. 24.502. Okay, and you know what to do. You've got a natural log, so we're going to exponentiate both sides. Those cancel, and I will get E equals, now you plug that into your calculator, that is going to be a large number. Okay, what we get is, I'm getting 4.3 do that on the calculator so you can see it. E raised to, now let's do the division. 7.13 divided by 0.291. Okay, that was the division, gave me that 24 number. Oop, didn't like that. I think I left a decimal place out. There we go. Because there it gives me. Now, be careful over here because this is saying it's 4.375 times 10 to the 10th. That's what this e to the 10th means. Okay? So, times 10 to the 10th. It is a very large, a lot of energy. Okay? There we go. All right. So, you've got some classwork to do, and I will see you next class.